Good morning, everyone. So, good evening. So now, so after food, so I always one feel very sleepy, right? So it's not good to talk about some serious science. So therefore, decide to talk about something, yeah, with some physics, but mainly is my own experience. In my past years, so I choose a name, journey to the quantum world. It's mainly our journey or the journey of our division or to the quantum world. Before I go into talk about details, I think I feel obligation to tell you something about our history of UITC. So the full name of UITC is University of Science and Technology of China. But also we have a nickname is United States Training Center because 30% or maybe more of our graduation and will go to United States to pursue their PhD study after they graduate from UITC. So our university was established by the Chinese Academy of Science in 1958. So this year, and within a few weeks, we are going to celebrate the 60th years anniversary of our university. So the mission of our university is to meet China's research need of a nuclear weapon at that time. Okay, so missiles and satellites. So we also have a joke, and our university only have two major. So physics is one major, and non-physics is another major. So our university is one of the best university in physics in China. Okay, so but in 1970s, because of the very bad relation at that time with the former Soviet Union and China. So our leader decided, okay, for the most important university should not stay in Beijing. So they should move to some small city so that if we have some war with former Soviet Union, probably we can keep the scientists alive and continue to do something good for the country's future. So therefore, we moved to Hefei in 1970. So now, and we have an institute for advanced study, one in Suzhou, very close to Shanghai, and also we have one institute for advanced study in Shanghai, which was established in 2007. So, and now I would like to give a brief introduction about our center. So our center is is a CAS center for excellence in quantum information and quantum technology. So which is jointly supported by CAS and the Ministry of Education. So we have very stable annual budget, which is about 150 million Chinese yuan for the annual budget. So which is hosted by UITC, but also include many top institutes and universities around China. So our headquarters is in Hefei, so not in Shanghai, but we also have a branch in Shanghai, which in our Institute of Advanced Study. So also we have branch in Beijing, and the people in Beijing mainly concentrate on theoretical study in quantum communication and topological quantum computation and quantum material. Because the Institute of Physics the CAS is very good in semiconductor physics and condensed matter physics. So in UITC, in our headquarters in Hefei, so we are working on various systems with quantum information processing with the photon, MV center, semiconductor, hard-coded atom, and so on. Also, we are working on quantum repeater, quantum communication, quantum sensor. So for our branch in Shanghai, is mainly is our division, so concentrate on free space quantum communication and also quantum computation and simulation with superconducting system and hard-coded atom, and also with single photon detection and so on. So, and our center is currently play a leading role in organizing the National Science Technology Project on quantum information in next 12 years, which is very much similar to European Quantum Technology Flagship Project. Our project will start from the end of this year within a 12-year budget, which is about, I think is 100 billion Chinese yuan for 15 years or for 12 years. So mainly concentrate on communication, computation, and quantum metrology. Okay, so now I give a few words about our division. So our division is mainly contained two parts. So mainly on quantum information processing with the photon and atom, including also some research about superconducting quantum computation. So for the quantum communication, we cover all the possible solutions now. So for the first one is free space quantum communication with satellite, and also quantum repeater with quantum memory and so on. So also we are working on a metropolitan fiber quantum communication network. So beside quantum communication, we're also working on quantum computation and simulation. So, and from multi-photon entanglement and superconducting qubit and atom entanglement, and also we're doing something related to arch code atom and simulation and so on. So we start to build our division since 2001, as I will mention later. Now we already have 27, principal investigators. So for example, this guy is a joint professor, Barry Sanders, probably you know him very well, and also Matthias and Wiedemuller. He also have part-time and position in our division. So from quantum optics to quantum information. So altogether, we are working on various topics. So now, I would like to share with you my own experience, how a young student, from young student to nowadays, we have a mid-sized division. So I entered into UITC in 1987. Then and later, after almost 10 years, I moved to Innsbruck. Then I also spent some time in Vienna. Then in 2001, we start to set up our division at that time in Hefei, and later on, I moved to Shanghai. So one of the reasons for me to choose physics as my major is because English or language or the other thing is too difficult for me, because it's really difficult for me. And all the chemistry, you have to remember many formula. So physics is much more simpler. You only need to remember few formula. Then if you know mathematics, you can deduce many other things, right? So I'm quite happy in my high school. So I decided to choose physics as my major. But unfortunately, in 1989, when I started to learn quantum mechanics, after a while, so Professor Dongpei Zhu was our, and teacher at that time for the quantum mechanics. So he gave a very good lecture, but I really totally lost. And especially, I carefully read the book and the lecture note by Dirac. And this is older book I stole and from our library. I keep this for myself for quite some years. But the thing is, I find out because physics is simple for me, but quantum mechanics is extremely difficult for me. So I could not understand how a cat can be simultaneously both in a live or dead state. How two space-like separated dies are always correlated. Then in my middle term examination, I almost failed to pass through the examination because I always thinking, I have no time to do the exercise, to do the calculation. So therefore, after a few years, in 1991, when I start to prepare my bachelor thesis, I think it's better I spend more time to figure out some details about the basic concept of physics, quantum theory. And this is my bachelor thesis. Here means the basic conception of quantum theory. So I perform a completely comprehensive survey about quantum paradox. So during that time, I studied the quantum entanglement. I talked to my supervisor, Professor Yung Zhang. I said, oh, it's very strange. If we perform distribution of entanglement, if someone performs some measurement before we perform the measurement, we will see no entanglement. So I write a Chinese article, send it to the Chinese Nature Journal. But I get no response. But after a few years, when Arthur Eckhart came to Innsbruck to give a lecture, I immediately got his idea. Because in my bachelor thesis, I also mentioned if some evil job in between to see our entanglement, then finally we do not see violation of entanglement. I still clearly remember when Arthur came to Innsbruck to give the public lecture, I got his idea within a second. So here I have a lesson. I mean, sometimes if you think something deeper, if you have some nice idea, you are not very far away from those giant scientists, right? For example, at that time, I'm a bachelor and student. I also already touched the edge of the physics of quantum key distribution and so on, right? So then, that means, because at that time, China is very difficult to perform experiments. If I only think about the Gedanken experiment, it's not possible to go further. So I think it's better to go somewhere to do some experiment. So in 1996, or in 1995, I contacted Anton Zilling to ask him whether he can provide me with a PhD position to do some experiment, because I think Europe is a great place to learn quantum mechanics, because most of the father or pioneer of the quantum mechanics are from Europe. So therefore, in 1996, I started my PhD study in Innsbruck. I fly from Hefei, actually from Beijing, from Hefei to Shanghai to Beijing, then to Innsbruck. Then I started my PhD study. So the funny thing is, because my background of my master's degree is theoretical physics, immediately after my arrival, so Anton asked me to perform some calculation. He said, you maybe try to perform some calculation. What will happen if we send 2 photons simultaneously onto a beam splitter? Yeah? So now everybody here know, I mean, we will have anti-bunching. If the 2 photons have the same position, then both photons will end up at the same output of one of the beam splitter. But then at that time, I see what will happen if, and this photon is entangled with another photon. So I perform similar calculation, then it's some sort of partial teleportation protocol. Because at that time, in China, it's very difficult to get the references. So when I joined Anton, I even have no chance to read the teleportation paper in 1993. So I feel so happy. I thought I find something great. Then I immediately go to Anton. I say, Anton, I find something new. I want to give a presentation during the morning a group meeting. Then after my presentation, so it's silent. No one asking me a question. So only Mihail Recki, at that time, the senior postdoc, he asked me, Jian-Wei, do you know quantum teleportation protocol? So you know, I don't know. So I feel so then, but Anton is very nice. And after our group meeting, he brought me to the post, and he said, yeah, so we are, I don't know. So he said, we are working on the experiment. Then I said, then I think it's so interesting. I really want to join to perform this experiment. So that's the whole story. I mean, why I joined the teleportation team. Then we were so lucky. Then I have chance really read this wonderful paper, because in China at that time, we do not have the money to buy the original version of physics review letter. So normally, only one institute is Institute of Theoretical Physics. They will buy the original version, then they will make the copy, then, okay, of course it's not good for the intellectual property, right? So, but then we have a chance, after some time, we have a chance to read, so the thing. So, thanks to this wonderful scheme, I also carefully studied this, and the paper. So here, 2 of them are here, right? So Gears and Charis, so our pioneer in the field of quantum communication. And Anton also showed me another paper. So today, Arthur is alone, but their paper will publish slightly later. But this is a practical scheme. They talk about entanglement swapping, right? But of course, in the original paper, they also discuss about the case, what will happen if the particle itself is entangled with another particle. That is, it exactly corresponds to the conception of teleportation of entanglement. So this is, for me, is the first time I start to know some basic conception of quantum communication. So it's in 1996. So after 1 year, and yeah, actually in November of 1996, Dick Baumist came to our laboratory. Then we worked together, and after 1 year, we did the first experiments about quantum teleportation. Of course, in the meantime, there are also some other nice experiments, like the Martini, but I think this experiment is essentially different from other realization, because here the input state can come out from outside, and also here we really develop a nice technology which we can interfere two independent particles, as I will show you later, which is also a foundation in the MDI, QKD, and so on. So now I came to some brief introduction about the QKD, and actually after my arrival to Innsbruck, and one student from Thailand, he is also working on QKD experiments, but at that time I think it's not so interesting to me. It's too simple. It's because it's only single particle experiments. Yeah. So of course, and we could also perform entangle-based QKD. So, and we know, in 1992, our pioneer already performed, according to Nicholas, he called this experiment as a minimal demonstration of QKD over 32 centimeters. At that time, okay, 32 centimeters is too, so this is too small. Then we don't need to use QKD, because I can direct talk to you, right? So I can come to your ear, then we can talk with each other. So I think one thing very important is we should extend the distance. And moreover, and because in 2000, yeah, and Passat, and also, and Norbert Lukenhout, he is also alone, they point out, and actually, there's still some loophole, we need to solve before we can perform and really secure quantum key distribution. So therefore, at that time, I think the most urgent thing is to solve the following and the following challenge. First of all, we need to find a way to extend the distance. Second, we need to improve the security. And finally, we also need to convince our user to use your system. But of course, before we are going to do some application, we first need to solve these two problems. So therefore, at that time, I think it is better, because we don't know whether we have some nicer way to solve a security problem. So I think it will be better, it will be safe for me to concentrate on long-distance solution. So how to do that? So, in 1997, and I took a course given by Ignacio Chirac. And in his course, he mentioned, actually, use the consumption of quantum repeater, we can go long distance. So what is the element of the quantum repeater? So as the paper published in 1998, so actually, once again, it depends on the original element as proposed by our pioneer, Charles Bernard, and Gilles, and also Arthur. So first of all, for example, how we can do if we want to perform long distance entangled distribution, so we can divide the whole distance into several sublocations. Then we perform entangled distribution between any two sublocations. Then by performing purification, then we can detail high quality of entanglement. Then with the help of entanglement swapping, we can connect long distance entanglement. But of course, we also need an element of quantum memory. So all the element of quantum repeater is 3 elements: entanglement swapping with high precision, purification with high precision, and also high performance of quantum memory. So why we need high precision entanglement swapping and entanglement purification? Because we have to make sure after your protocol, so the quality of entanglement can increase. So this is very similar to the error correction. If the precision of error correction is not high enough, then error correction won't work. So then I say, okay, maybe this is something what we need to concentrate. Then therefore, in 1998, we performed the first demonstration of entanglement swapping. But at that time, so the fidelity is very lower. We cannot demonstrate it's good enough for long distance entanglement and distribution. So it's only after some years, in 2003, we use another method we meant to perform high precision, fault tolerable intense swapping. So that's means and our way toward long distance quantum communication. So we perform the first one is high precision intense swapping. So the funny thing is, in the beginning of 2000, so one afternoon, Anton came to my office. He said, Jian-Wei, I just attend a conference. During the conference, and Ignaz Reich are talking about entangled purification. He said, this is a very urgent thing we need to do. And here is very, very important in long-distance quantum communication. So, and once again, so you see, so all this work, so I'm strictly following our pioneer step and step to go, right? So the idea was, and also suggest for purification by Charles and Bassan and so on, and also by Arthur and Deutsch and David Doyle and so on. So in the same years, they have more or less the same idea. So we should perform purification. So then, during the in the East of 2000, I paid some time to read the original paper by Charles and Bassan and Arthur Eckhart and so on. So the paper to me, because at that time I already and real and experiment. So it's difficult for me to understand so complicated procedure. But of course, I spent one day, finally, I understand the idea. But however, the original intense purification scheme requires C0 operation between independent photons. But we know, so interaction of two independent photons is negligible. So it's very difficult to perform C0 operation. But after some day, I come to my mind, maybe we can use a polarizing beam splitter. So just lean optics to perform the parity compression. So which is the same as somehow in the purification protocol, actually we do not really need a C0 operation. What we really need is a parity compression. So therefore, I think PBS is good enough. So therefore, and during East of 2000, I find this skin or use lean optics. But then at that time, I was okay, probably this skin is so simple, we should wait for a while so that we can prepare the experiments and we publish the result. But unfortunately, and after a while, we read the paper by KLM. So Kinnear, Lafran, and Melbourne. They have the efficient quantum computation scheme and with lean optics. So at that time, and actually originally I suggest to, for my theoretic science, okay, we cannot wait. We should submit our paper immediately. In the original version, I also with the name of intense purification for quantum communication with lean optics. But Anton said, well, lean optics is too specific. So we want to make the scheme more general. So he deleted the word of lean optics. So now, yesterday I looked into the citation. So the lean optic quantum computing now already be cited for 5,000 times. But for my paper, it's only cited for 600 times. But if I leave and keep the lean optics word, maybe the citation can be much higher. Because afterwards, the C0 operation and all the other operation is closely follow my scheme. So one of my lessons is, for a young person, should not always follow your supervisor. You should have your own idea. That's something I would like to mention here. So, and here I want to mention one guy. He is also learned, is Xianbing Wang. And Xianbing Wang mentioned to me once, and he also tried to read the two original papers about purification, but he also got lost. But finally, after he read my paper, then he really understands original paper. I will come back later because due to this communication afterward, they asked me to perform and the very first or some of the decoy experiments. Yeah. So because of our purification scheme, after a few years effort, so in 2003, we managed to perform the high precision fault tolerable intense purification experiment. So the precision is very high, such that we can prove fault tolerable in tank purification is possible. Yeah. But till now, so far it's very good. In tank swapping, purification can be done with linear optics, but how about quantum memory? Quantum memory is still the botanic. So at that time, I decided to take some challenge because I am a photonic person. I know nothing about atom. So I decided in order to do quantum memory, I really need to learn something about the cold atom. Then I make a difficult decision. I decided to go to Heidelberg and to collaborate with Jörg Schmidt-Meyer to find some nice way to achieve quantum memory. So, okay, and before I continue my story about quantum memory, I will come back because I follow the timeline, right? So as I just mentioned, due to the photon number splitting attack, so the security distance of QKD is very much limited, as pointed out by our pioneer. So in the fiber is about on the order of a few tens kilometers. But a few tens kilometers is not enough for practical quantum communication. Because if in the city, you can just drive a car to meet him within the coffee bar, then we can already achieve the same goal. So we have to solve the same. So thanks to these two guys, Hao Kuang and Xiang Bin. So in 2004, and they find a practical way to solve the beam split attack with realistic device, the so-called decoy state QKD scheme. So by which they send pulse randomly with intensity P1 and P2. So because I know Xiang Bin very well, so after his paper, he immediately came to me, yeah, probably we can and collaborate to perform this experiment. So we were lucky enough, and in 2007, several teams independently performed, a decoy state QKD on the order of 100 kilometers. So, and later on, we extended the distance to 200 kilometers. So we are so happy, so probably one of the major security loophole has been solved. But this guy, this bad guy, he said here, so he will know, the story is not yet finished. Because of imperfect single photon detector, so he can exploit the so-called blind attack, by which one can fully control detect by specially tailored strong light. We are feel so bad. Because we are happy, but then this guy make us feel so bad. But once again, thanks to Hao Kuang, and he proposed a scheme, the so-called measurement device independent QKD, and which is immune to any attack on detection. He proposed this scheme in 2012. So here you can clearly see, we really need interference of independent photon. So this technology has been developed in the first quantum teleportation experiments, right? So, and therefore, if we really have such a thing, and even your device, your measurement device is made by North Korea, then these two guys can still talk safely, right? So then, actually, and this guy, Xiongfu Ma, is also alone. He came to me, he said, okay, maybe you can perform this experiment because you already have the key technology and you can achieve two-fold interference between remote stations. Then we said, okay, yes. So here, I also would like to mention one good thing. Xiongfu Ma is from the same country as me. So many years ago, when I'm still a postdoc in Vienna, I went back to my high school to give a public lecture. So by chance, Xiongfu Ma was in the audience. Then he think quantum information is quite interesting. Then he chose quantum information as his major. Then after some years, he came back to me, asking me and helping me to perform the MDI QKD experiment. So it's also another good lesson. So it's always good to make some public distribution of your own research. So we start to do this experiment immediately. So here we need to make some high precision interference technology. So in this experiment, we managed to achieve a relative time jet after 100 kilometers, less than 10 picoseconds. So from 2013, we managed 50 kilometers. From 2016, we managed to over to 400 kilometers. So now, we are happy. Within the city, is good enough with MDI QKD or with such a thing? Okay, so what is the future challenge? So as pointed out by Nicolas Gisson, so I just cite you, so you comment. Due to absorption, we will have a huge photon loss. So for 1,000-kilometer commercial fiber, even with a perfect 10 GHz single photon source and ideal detector, only 0.3 photon can be transmitted on average percentually. So which means if we do not find a better way, so quantum communication will only be limited in the city. So can never be go outside, really can be a very useful technology. So one of possible solutions, as I just mentioned, is to use quantum repeater and quantum memory. So one of the main focus we need to solve is the so-called quantum memory. So in 2003, at that time I'm still very young because 15 years ago, we started from empty. So we started from thermal atom, but finally we find out thermal atom is not a good one. Then we are forced to go to cold atom. So here, so you see, all these guys are still alone. So they are, at that is also very young. So only, and this means 7 person, we start to construct our quantum memory experiments. So the one of the scheme of the quantum memory was proposed by Lumin Duan and Lukin and Serac and Peter Zoller. So here show the basic principle. So we to have 2 atomic ensemble which can be cooled on. Then if we shine in sunlight, then suppose one of the atom is excited from the ground state to another state. Then by combining these 2 excited photons on the beam splitter, then depending on detecting one and only one photon, then we have focus state entanglement. And because if this photon is from up mode, then we know here is in the excited state. This is in the ground state. But if this photon is from lower mode, we know here is the ground state, here is the excited state. Then we can prepare ground, excite, ground. Oh, so there's some mistake. Okay, sorry. And this kind of entanglement. But we have some drawback in this scheme. Because here, if we want to go to long distance quantum repeater, which means we have to make the phase stabilize on the order of a few tens nanometer. Moreover, in all the formal experiments, for example, performed by and Kimball and all the other group, so the lifetime at that time is still very short. So at that time, so the lifetime is very short. So and moreover, because we have many vacuum ton and vacuum ton, so the error rate will grow rapidly with the distance. So and after a few years effort, we find a better scheme by Bo Zhao, and he suggests we use instead of using single photon interferometry, we could use 2 photon interferometry, then which is very similar to entanglement swapping. So in this configuration, we can prepare the polarization type of entanglement between atomic ensemble and a single photon. Then in this case, so you can see, so the phase stability can be relaxed from sub-wavelength 100 nanometer to the order of a meter. So with the 7 order of and relaxation. And also in this case, the vacuum ton is no more dominant. And also the efficiency is much more higher. So since 2003 to 2008, finally, we have some good result. So we performed the first atomic, so BDCZ type of quantum repeater node. So we first generate atom-photon entanglement, then we send the photon through a fiber, which is connected by 300 meters. Then we perform a biostate measurement. Then we can entangle these 2 atomic ensemble. This one was performed in 2008. But we still have lots of trouble there. First of all, the lifetime is very short. And the second of all is the retrieve efficiency is very lower. So in order to really make, for example, if we want to build up a 500-kilometer quantum repeater, so you can see if we fix the retrieve efficiency, so the lifetime has to be increased from the 1 microsecond to the order of a few tenths second, which is so difficult at that time. So we need to find some good way. So from 2008, we gradually find them and improve the decoherence mechanism. So first of all, in order to cancel an effect caused by the residual magnetic field, we use the clock state, which is insensitive to the magnetic field. And also we use collinear recoil and method to enhance the wavelength of the spin wave. Then we can increase the coherent time by order of 2. Blah, blah, blah. After many things, then we get some improvement. Till to 2012, we can see we already have some significant improvement. But still, the required lifetime still need to be extended about 2 orders of magnitude. So finally, so very recently, so 2 years ago, and we, with the help of ring cavity and optic confinement, we can really avoid most of the decoherence effect. We managed to achieve a lifetime of 200 milliseconds, and with retribution about 70%. So you can see we already touched the bottom point. So to support 500 kilometer quantum repeater. But of course, for a realistic realization of quantum repeater, according to some of my friends, like Yunshi Yamamoto, he said it will be a science fiction. He thinks the difficulty to build up a practical quantum repeater might be the same as the quantum computer. But I don't think so. I think maybe within 10 years or a little more time, we should be possible build up some sort of practical quantum repeater, if we are lucky. So, therefore, since 2003, I think it will be safer if we choose another a way to achieve long-distance quantum communication. So in 2003, and we handing a proposal to suggest to perform some ground test about the free space quantum communication. For the reason is because, first of all, and in the outer space, we have no obstruction from a temperature curve and a barrier. And moreover, so the horizontal allosphere is only about 10 kilometers of, so the vertical allosphere is only about 10 kilometers of horizontal and allosphere. And also in outer space, we will have no observation and no decoherence in outer space. So here, when I talk about this idea with Anton, Anton mentioned to me, and he said he has a nice discussion with Nicolas. So Nicolas have a question, and he said, would it be possible to set the quantum satellite before his retirement? So Anton want me, we could try, but we should take the risk. Yeah, he say. So I mean, in the beginning, we are very cautious. And in 2000, okay, I just go to the next slide. So in 2003, we only asked for 2 million Chinese yuan. So we said we want to try whether it's possible as our entangled photon can penetrate the effective thickness of allosphere, right? So then it turns out it's very successful because after 2 years we managed, we can perform intent distribution and over a 13 kilometer and free space channel. Okay, then and we go to the funding agency. We say now we want to do a little bit more for the next step. So we ask for 10 million Chinese yuan. So we go to and Qinghai Lake. Then we also perform some further experiments. So we just try to perform the teleportation intent distribution on the order of 100 kilometers. Then also we try to calculate the loss of the satellite to the ground channel is about 40 dB or 70 dB. We find out it's possible with the help of adaptive optics. Then, and we really become more and more confident. Then we go to get more money. We say, okay, now we really need to make some ground test model. We get 50 million for the ground test. So I mean, finally, from 2013, and we finish all the ground verification of satellite to ground QKD. Then we are allowed to start our, final establishment of our missile satellite. So here I want to convey, one of the messages I want to convey, if you want to do something risk, it will better start from some minor thing, then go step by step, if you can really go to next and next step, then you will always manage to get support. But not in the beginning, just say, okay, I want to get, and this money. Then you will never succeed. Yeah. So it's really a long-term project. So when we start in 2002 and 2003, so he is a main person take care of the engineering stuff. And Chen Zipen, at that time, he is still very young, you can see. And also this lady, she is blonde and also very young. But now, and his hair is already white. But unfortunately, my hair is still black. I don't know why. Maybe. So, okay. So our team and graduate Pan from a few people then, and before we launch the satellite, we already have so many people work together. So it's also very important we can collaborate with engineer. But the thing is, scientists and engineer and always have different opinion. Scientists want to always change your design to get the best performance. But engineer only want to keep the safety. He said, no, we should not change your setup. But the thing is, we always find some balancing. Without the balancing, if only, follows engineer, our satellite actually finally will not succeed because they want to make the quality as stable as possible. Then our final key rate will be 2 orders of magnitude lower than what we finally achieve. Because after the launch of satellite, we have some other problem. If without the scientists' strict requirement, then I think it will be difficult to succeed. Yeah. So from 2002, after 13 and 14 years effort, so in 2016, and we launched the satellite. Yeah. So why we call our satellite as Misuse? So Misuse is and lived in an ancient time. He lived about 2,400 years ago in China. So he is a philosopher, but he is also a scientist. So here I would like to mention several factors. And actually, he was the person who realized the first pinhole image experiment in the world, demonstrating that light travel is in a straight line. So here is his, basic design. So here is and how he draw a hole, then he stand outside, then the sunlight will come, then he will see his image will be, reversed. And moreover, he has many ideas. So he is universal love and peace. He does not like war. So he has, he always, and because at that time in China, we have many small countries. So when the country want to have a war, so he always go to and pursue the people. No, you should have no war. But then say, okay, I can, and invade to other countries. Then he said, I have some high technology. I can help the weak country to protect them. Then they play the game. So he is very good. In peace. And also, he have several nice consumption. So he also have an original conception about the quanta. So here is his original sentence. 端体之无序而最前者也. If I translate it into an English, and he said, and 端, or we call it quanta or particle, is a smaller unit which cannot be divided. So this is one of his opinion. And also, and this is very much the same as and Democritus, he also proposed atomic consumption. Atoms cannot be divided. Moreover, he also have another very interesting consumption, and which is very similar to inertia, so law of inertia. So he said, 直以久也，无久之不止. So he said, in the absence of force, the movement will never stop. So for this reason, I just, okay, maybe it's a good idea, choose his name as a nickname of our satellite. So Misuse satellite has 3 missions. So for the first one is to perform key distribution. And for the first experiment, we managed to have about 1 kbit per second. But very recently, and this key rate has been increased by to 400 kbit per second. Yeah. So from last year to this year, we get significant improvement by improving our adapt optics. So moreover, we also perform some experiments, for the test of content non-locality. But of course, while this is one of our idea, but our long-term goal is we want to show the possibility to perform entanglement-based QKD. So we are going to perform these experiments from next month on. So hopefully, we can finish this experiment by the end of this year. Of course, we have another one, is just for fun, is for content teleportation, and so on. Then, soon after that, in last year, we also performed, QKD with Vienna Station. Then very recently, and we already have a link with and Apollo and in Italy. Then hopefully in the near future, we could collaborate with our colleague, and we can see the possibility to construct a very basic, ground and network with the help of content satellite. So of course, okay, so as I just mentioned, so for long distance, now we have two major solutions, content repeat and free space. And also for security, we decoy the QKD, MDI, QKD, and also some other method, blah, blah. Then it's time, and also to do some practical application. So from 2009, and we have a small network in Hefei. Then in 2012, and this network is still running, which is the largest, over 46 nodes and so on. So, very recently, last year, we established the Beijing-Shanghai content backbone network with the help of and trustful relay. So, of course, in the future, we hope to use content repeater. But as a template solution, is already better than the traditional way. So, which test better for content, for content communication backbone. So the whole distance of the fiber is 2,000 kilometers. And also now is currently for some financial application and public affair and so on. So people say, okay, the satellite, if the weather is not good, so how can such a thing can be really useful? But if you talk to the and cryptography people, they said because for the highest and secret, and normally we need to use a one-time pad. Then how to do that? So normally they will ask people. For example, if the Ministry of Foreign Affairs in Beijing want to contact with the Chinese embassy in Vienna, so normally they only use a one-time pad method. So how to send the key? So normally they ask two people, take airplane, then bring the key to there. But the refresh time is on the order of 12 months or 18 months. It takes very long. But with the satellite, although sometimes the weather is not good, but I think on average, not every day, but at least every week, you can distribute the key. So for some small user or for some, specific user, such a method already can provide a very useful solution. So, and the second thing is, it really, and to make the QKD really useful thing, and we need to convince the people our system is really secure. I think it will be important in the future for our community to start to work together to make standard. So, this is something what we should also do in the future. I think it will better we collaborate all together. So what we are going to do in China, I only will talk about content communication. So the first of the thing is, we want to perform so the entanglement-based QKD with, and with entanglement distribution. And this is something what we are going to do. We hope we can finish and within the year. So the second thing is we are going to launch several low orbital satellites, small satellites to construct a content constellation. They also combine with, and after the Beijing-Shanghai backbone, so we already have a plan. We will build up a national-wide, content network, step by step. Okay, so first here is Beijing to Shanghai, but we will build up from Shanghai to Wuhan and so on. It will be, then will be, it's not a backbone, then it will be a circle, content network. So we could have space and ground integrated network. But of course, and one precondition is we hope whenever you have a constellation, then the system must be work on the solar radiation background. So in 2017, we already show in principle it should be possible you can develop such a system which can work during the day, by exploiting the dark line of the sunlight. And also, we are going to exploit, our satellite network and optical communication to, and perform and the so-called global and price-time information sharing network. Because together with optic atomic clock and plus with optical frequency transfer, so such a time sharing method can be much better than the microwave. And of course, we're also performing some experiments, following the idea as suggested by LAFA, to see whether we have some gravitation-induced anti-correlation of entanglement. But of course, unfortunately, so far we did not see anything on the 10 standard deviation. We will see, what is going on in the future. Okay, and because I think, so I just mentioned the last thing. So last thing is within 10 years, in China we will have a moon and a plan. Then also we will have a space station. Then we have planned, we are going to launch a satellite in the Lagrangian point. So in this point, because the gravity cancel each other, so and also the distance is only of 1 light second. If we can perform such in-time distribution, it could allow us to perform large-scale biotest with a human observer. So we also already performed some ground tests. For example, the loss, the calculation loss between the satellite, between Earth and the Moon will be on the order of 100 dB. Now with the loss of 103 dB, it should be possible to perform such a thing. Okay, I think before you get tight, it's better I finish my presentation. So thank you for your patience, for your attention. So I think because after dinner we feel tired, we still want to show some music exhibition. So we will have some Chinese music for the remaining our dinner. Thank you.
Want to say something? Okay, please enjoy.